Hello, this is Professor Gibson. Welcome to video on Chapter 5, Section 3 for Math 114. The title is Linear Equations, and we're going to be exploring more about linear equations. In this first part, you're given information in several different ways and asked to draw equations and answer questions. The part I wanted to focus on here is the fact that linear equations, are often used to model things in the real world, and we have to use judgment about when it's reasonable to use them. All right, so let's look at this first question here. Suppose your dog weighed 2 pounds at birth. All right, 2 pounds at birth, and it weighed 14.8 pounds 1 year later. Based on these two data points, find a linear function that describes how weight varies with age. Use this function to predict your dog's weight at 5 and 10 years of age, then comment on the validity of the model. All right. So they tell us, if you read the question here, the equation used to model the situation is where W is the weight of the dog and T is the time in years. So they want us to use W and T instead of X and Y. So our usual slope-intercept form, where we would write Y equals mx plus b, what they want us to do is write W equals mt plus b. So m, the slope, will still be the rate of change, and b is still going to be the initial value. Okay? All right. So m, right, is the change, this time in W instead of Y. Change in W divided by the change in T. Okay. So W at the high end is 14.8. Starting value is 2.0. And T is after 1 year, and we start at 0 years, right? 1 minus 0. What we get from this is 12.8 over 1, or m, our slope is 12.8, right? This dog gained 12.8 pounds in his first year. Really, that's not very, that's it's a 14.8 pound dog. It's not all that big, right? It's on the smallish side. Okay, but now we need to finish writing our equation. W equals, so our m, our rate of change, is 12.8 t. And remember, our b is the starting value of the w, right? Well, the starting value was 2 pounds. So we don't have to really go through anything else, it's just plus 2. All right, there's our equation. Now, the next thing it says, use this function to predict your dog's weight at 5 and 10 years. So really, to understand this question, you've got to know a little bit about dogs, right? Dogs are pretty much full grown at 1 year. So the idea that the amount of weight gain from year 0 to year 1 would have anything to do with from year 1 to year 5 and year 5 to year 10 really just doesn't make any sense. Let's plug the numbers in and see how that works out. So let's just stick in a 5, right? Stick in year 5 for the time. That's 64 and 2. Dog is now 66 pounds. Well, there's lots of dogs that are 66 pounds, but this dog weighed 14.8 pounds when it was 1 year old, pretty much full grown. It's not going to go to 66, right? That's completely wrong. That's completely unreasonable. And at 10 years, it's even worse, right? That's 130. So now we have a dog that weighed 14.8 pounds when it was full grown, and now he's 130. This dog can't walk. In fact, it's probably already had a heart attack or is getting ready to, right? So the point being, the numbers work in their age range, right? We get a number at year 0, right? What we give us here is they give us a number when the age equals 0, and another one when it's 1. So those numbers work well when you're at 0 or 1 or close to it. And the further away you get, the less meaningful they are. You can't keep using, you need new data when you get farther away from your data, okay? Let's look at another example. Find the fastest growing city and write an equation that models the growth. What is the rate of change? Well, if you look at the numbers here, the biggest percent is right here is 26.1. This is Houston, Sugar Land, Baytown. I take that to mean essentially Metro Houston. So this percent of change, if you divide it, this is year 2000 and year 2010. So really what that turns out to be is the percent change over those 10 years. So that's that would be the rate of change for the population, right? Remember, a percent is always based off a reference, and the reference value is the starting population here. But that's the percent change based on the population. If you were to write, right, we could make an equation on this, okay, right? Use our usual t since the beginning thing, right? So t equals 0 for the year 2000, t equals 10 for the year 2010. We've got our population values here, right? Population at t equals 0, population at t equals 10, and we can make an equation, right? The b, the slope intercept is going to be that, it's going to be this number here. All right. I'm not doing that. You would have to answer this question, but I want to focus on the thing here is, according to the model we just made, what was the population in 1990? All right. So we've got population for 10 years, 2000 to 2010. We want to use it to project the data of the population in 1990. This really doesn't make sense. Remember the dog up above? Okay. How much sense did it make to use the age of the dog 10 years outside the data we got, right? We got an answer that was total nonsense. Same thing here. I mean, I don't know how fast whatever affects the population growth of a city, but I wouldn't, I mean, something that's only 10 years wide and then 10 years out, further away than that, I think that's nonsense. And this one over here, this one's almost hilarious. How about the population in the year 10, right? As in, back around the time when Christ was born. If you, any model you make here, you stick that into it, right? Remember t equals 0 at the year 2000, right? So this would be like t equals minus 1990 years. I'm almost sure you'd get a negative population. That just doesn't mean anything. And even aside from sticking in the numbers, this is just way too far away from where the data is. It's not going to make any sense. Okay? So those are the kind of things. You're going to model the data, you're going to make the equations, but you're also going to be asked things about what are the limitations, what is this, where does this make sense? Okay? Now, moving away from the word problems a little bit, there are several questions, just kind of review, hopefully, of drawing lines and working with lines, And I want to cover up some special cases here. So first, here's this one, 5x plus 2x equals 28. The first thing I want you to notice here is there's only one variable. These are both x's, okay? There's no y in this. So anytime you have an equation that's got both x's, it's only got x in it, it's a vertical line. All right, it's a vertical line. So let's go ahead and solve for it. 5x plus 2x is 7x equals 28. Divide both sides by 7. X equals 4. If you were to graph this, it's a vertical line. X equals 1, 2, 3, 4. It's a vertical line right at x equals 4. The second one, 8y plus 12 equals 2y. Same thing again in the sense that there's only one variable, right? There's only one variable. This time it's y. 8y plus 12 equals 2y. When there's only one variable and it's y, this is going to be a horizontal line. Okay? Horizontal. All right, well, let's solve for it. So we want a y equals, right? Subtract 8y from both sides, leaves me with 12 equals 2 minus 8 is minus 6y. All right. Divide both sides by minus 6 to isolate the y, right? Y equals minus 2. Remember, it's a horizontal line. So if you drew a graph, minus 1, minus 2, you'd get a horizontal line where y equals minus 2. All right. So a lot of the slope rules and stuff don't really work when there's only one variable. You just got to remember, if there's only y's, it's horizontal. If there's only x's, it's vertical. All right, two more things I want to touch on, just as reminders. Some of the equations, some of the questions are going to tell you the lines are parallel, like this one. Write the equation of the line that is parallel to y equals minus 2x plus 3 and goes through this point. Well, parallel, if two lines are parallel, parallel lines have the same slope. Right? So we're doing our y equals mx plus b thing here. Right? Slope-intercept form. This equation over here is also y, and it's minus 2 for the slope, right? So we know the equation we're looking for is going to have our slope of minus 2. Okay. Then they give us this point, 1 minus 3. What you can do is just stick in the value, stick it in, and solve for the b. Minus 3 for the y equals minus 2 times 1 plus b. Minus 3 equals minus 2 plus b. Add 2 to both sides. B is minus 1. So just stick the minus 1 in here, and our final answer is y equals minus 2x minus 1. Last question. Perpendicular lines. All right, two lines are perpendicular. When lines are perpendicular, this is the symbol for perpendicular. They're slopes. Right, so you got one slope and another slope. Right. Anyway, their slopes are opposite reciprocals. What that means is if the first slope, say, is 3/4, the second slope is opposite that, and then reciprocal means flip it. The first slope, say, a whole number, one opposite that, and then the reciprocal of the whole number is 1 over that number. Okay, so for this question over here, we want the line that goes through the point 2 minus 2 and is perpendicular to the line 6x minus 2y equals 8. So first thing we're going to have to do, 6x minus 2y equals 8, is put this in slope-intercept form so we can read the slope off. All right. So we need to solve for y, subtract 6x from both sides. Now to get the y by itself, divide both sides by minus 2. Over here we get y. Now remember, we have to divide both the minus 6 and the 8 by the minus 2. So minus 6 divided by minus 2 is 3x. 8 divided by minus 2 is minus 4. So this is the slope of our original line. We want one that's perpendicular to it, right? So if the original one has a slope of 3, perpendicular, then it's going to be opposite, and then 1 over that, 1/3. So there's the slope of the line I'm trying to find. Okay, so getting started, we've got our first step, y equals minus 1/3 x plus b. I think I'm going to leave this one for you to finish, or you can just let it go. You know what to do now, right? You stick in the point 2 minus 2 here. Right, stick in 2 for x minus 2 for y, solve for b, and then plug that back in here. All right, that's it for this one. I hope you find that helpful.